Hey everybody, we're going to start another topic here. We're going to start working with matrices or arrays as they're often known in this lesson. And they have a lot of applications, lots of applications in the computer sciences. And we'll take a look at a couple of the simpler ones in the next few lessons. One of the more important applications of matrices that I just want to bring to your attention is on your screen here. Matrices are ultimately what are used to do all the mathematics of really good computer graphics. So it goes way beyond the skill level that we can develop. But there's a real simple example shown on your screen here. The original little house shape is shown there in black. And by using matrices, you can change the relative appearance of that image. So it can either be flipped or rotated. And in fact, that's one technique for changing the perspective inside of video game graphics is you enter a virtual environment and your perspective changes as the active player. That can be done using some pretty complex matrices. But instead, we're going to start out with a simpler set of information here. I'm going to start out by showing you what a matrix is, how to perform basic operations on matrices, and then we'll build on that for a few lessons. So let's get started. So first of all, some terminology. Um, any rectangular array of numbers or grouping of numbers is called a matrix, and those two names are pretty much synonymous. An array or a matrix mean really the same thing. Matrices are simply the plural of matrix. So one matrix is a matrix, several of them make up matrices. So this matrix on the left is a real simple matrix. It just gives the high temperature in Fahrenheit for the first 3 days of December. So you can see here on December 1st it was 37 degrees, on December 2nd it was 33 degrees, and on December 3rd it was 41 degrees. So just numbers in the matrix, we don't put words in there, but there's definitely some defined meaning to the values in that matrix. Here's another one. This matrix gives the latitude and longitude of La Crosse, Wisconsin. So the latitude of La Crosse is 43 degrees, 48 minutes, and 48 seconds. And the longitude is 91 degrees west, 13 minutes, and 59 seconds. So again, just a box of numbers unless we know what those things represent, and then it carries some meaning. Now, some matrices are skinny or flat. They're pretty small. If you have a matrix like these that only have one column in them, like this one, or one row like this one, so it's really barely a rectangle and more of a line, we call that a vector. And vectors have lots of applications in the sciences and mathematics. But even though a matrix that is flat or skinny like that with one row or one column is called a vector, we don't really distinguish. We're just going to continue to call it a matrix. It's just important if you were to go on and take a physics class that many of the things that you would learn about vectors work really, really well in conjunction with matrices, but we'll leave it at that. Okay, here's some real mathematics stuff. The size of a matrix is always given by the number of rows and columns, and it's important to get that order right for some of the work we're doing just a little bit. So this matrix right down here, we would call that a 2 by 3 matrix because it has 2 rows and 3 columns. So we always have to give the number of rows and then the number of columns. Switching the order will create problems for the math we're going to do shortly. And for some notation here, matrices are named or assigned a variable always using capital letters. So you've done algebra before. We've done algebra in this class. And usually a variable represents one number, but a capital variable can often be representing a whole matrix or a whole array of numbers. But the values inside a matrix, those are called elements. And they are always identified using one of two common methods. You can use subscripts like shown here. A sub 1, 1, that's the value within matrix A in the first row and the first column. A sub 1, 2 is the value in matrix A in row 1, column 2. That would be 5. And same idea, A sub 2, 1 would be the value in matrix A row 2, column 1, which is -2. The other notation that is often used is a set of parentheses to give sort of the coordinates in a sense of that matrix. So A parentheses 1, 1 means matrix A entry in row 1, column 1. Well, that would be 6. Same idea. Matrix A, row 1, column 2 would be 5, and so on. And even though matrices might look different, matrices can be equal to one another if they're the exact same size, so same number of rows and columns, and all of their entries or elements are the same. So even though these two matrices look slightly different, their entries are equal. In the top left, 1 is equivalent to 3 over 3, and in the bottom middle, 4 is the square root of 16. So those two matrices are equal. Okay, let's take a look at some simple matrix operations here. We're going to start by adding and subtracting matrices. The key here is matrices have to be the same size in order to be added or subtracted, and all we do is combine corresponding elements. So let's take a look here. We want to find the matrix D plus E. All we need to do is add corresponding elements. So in this case, that means we'll have 2 plus 1 in the top left, 6 plus 9 in the bottom left, 4 plus 5 in the top right, and 8 plus 3 in the bottom right. And that's going to be our new matrix. D plus E is then the matrix 3, 9 in the top right, 15, and 11, and that's all there is to that. And I'll bet you know exactly what to do to find D minus E then. If we take D minus E, we're going to subtract corresponding elements. Make sure that you respect the order here. So we're taking D minus E, that's going to be 2 minus 1, 6 minus 9 in the bottom left, 4 minus 5 in the top right, 8 minus 3 in the bottom right, which leaves us with elements for our matrix of D minus E, 1 in the top left, -1 in the top right, -3 in the bottom left, and 5 in the bottom right, and that's all there is to that. I'll give you a practice problem with that in just a minute, but let's look at another basic operation. Scalar multiplication is done by taking any matrix of any size and multiplying it by a constant numeric value called a scalar. So same two matrices here, D and E, we'll use D first. Then 3D is simply taking all the elements of D and multiplying them by 3. So that becomes 3 times 2 in the top left, 3 times 4 in the top right, 3 times 6 in the bottom left, and 3 times 8 in the bottom right, which means the matrix 3D is given by 6, 12, 18, and 24, and that's all there is to that. Negative E is like saying -1 times E, so that means we're going to multiply every element of E by a -1. So that's going to be -1 times 1 in the top left, -1 times 5, top right, -1 times 9 in the bottom left, and -1 times 3 in the bottom right. So negative E then is just as shown, -1, -5, -9, and -3. Okay, there it is. Those are pretty easy operations. Let's take a look at one more. It's a fairly simple operation before we look at some more complex operations. Transposition is done by swapping all the rows and columns for a matrix. That means the size will change if it's not square. So let's take a look at F. F is a square matrix, 2 rows, 2 columns, and so the result will be 2 rows and 2 columns. Notice that the superscript of T represents the transposition of a matrix. And so the top row in F becomes the first column in F transposed, and the second row in F becomes the second column in F transposed. Now, when the matrix isn't square like G, it's going to change the size. G is 2 rows by 3 columns, but the transposition will be 3 rows by 2 columns. And so the top row here, our first row, 4, negative 5, 8, will become the first column, 4, negative 5, 8 in the transposition. 1, 9, negative 3, our second row, becomes the second column when it's transposed. Okay, I'd like you to take just a minute and perform these three operations. I've given you a matrix M and N. Go ahead and do those. Pause the video right now while you work them out and unpause to see those solutions and make sure you get these right. Okay, let's see how you did. For our first one, n minus m, be careful of the order here. It would be tempting to take m minus n based on the order I gave you, but n minus m are going to be the values of n minus the values of m. So that's 0 minus 8 in the top left, 11 minus negative 6 in the top right. Be careful of your signs there, and so on. Negative 2 minus 4, 1 minus 5, 7 minus 0, and negative 1 minus a negative 2. And if you do that, then you'll end up with negative 8, negative 6, 7 in the first column, and 17, negative 4, and negative 1 plus 2 is 1 in the bottom right. That's what you should get. And again, we started out with two 3 by 2 matrices. We end with a 3 by 2 matrix. 8n, we're going to multiply all the elements of n by 8. So 8 times 0, 8 times negative 2, and 8 times 7. 8 times 11, 8 times 1, and 8 times negative 1 gives us a new matrix 8n of 0, negative 16, 56, 88, 8, and negative 8. If you got those, nice job. And M transposed. We're going to take M, and the first column will become our first row. So we have 8, 4, 0 across the top, and our second column, negative 6, 5, negative 2, becomes our second row, negative 6, 5, 2. And M was a 3 by 2 matrix, so M transposed is a 2 by 3 matrix. And hopefully you got that result as well. Okay, our next operation is a little bit more tricky. Watch our process here in the next couple of examples carefully. We're going to be using this operation a lot in the next few lessons. Two matrices can be multiplied together only if the number of columns in the first matrix matches the number of rows in the second. Now here's the thing. Notice that these two matrices are not the same size, and it's common for people to think that you would multiply matrices by doing what we did with addition and subtraction and just multiply corresponding elements. That's not at all how multiplication works. There's nothing useful that comes from just multiplying individual elements. Plus, they're not the same size, so it's not even clear how we would do that. So I'm going to start out with a real simple example here. Now, these are both technically vectors, right? This one only has one row and this one only has one column. But that's just going to provide an easy example here. So our first matrix is one row by 4 columns. That is a 1 by 4 matrix. The one on the right is 4 rows, but only one column. So that's 4 by 1. So what we always have to check when you want to multiply matrices is, are these two middle numbers the same? That is to say, the number of columns in this one is the number of rows, 4 columns, does it match the number of rows in this one? And since they are equal, then we can multiply. If these two middle numbers are not equal, we cannot multiply. And what's more important is the two outer numbers, the 1 and the 1, that tells you what the size of your new matrix will be. So we're going to get a result here that, believe it or not, is going to be a 1 by 1 matrix. So how can that possibly happen? How do all these numbers become just one entry? Here's how. What we want to do is we're going to take this row and we're going to multiply each element in order by the column in this matrix. So I'm going to take the first entry, 5, and I'm going to multiply it by the first entry here, which is 1. 5 times 1. And then to that, I'm going to add the second entry product, 6 times 2. Parentheses there to make it a little more clear. And I'm going to add on the third entry product, 7 times 3. And then I'm going to add on the fourth entry product, 8 times 4. That's called the dot product of these two vectors. Dot products are really important for a lot of reasons beyond what we're going to look at, but we always need to find multiple dot products when we're multiplying matrices. Now, if we add all these together, that's really 5 plus 12 plus 21 plus 32. And if you add all those up, you get 70. And so we do get a 1 by 1 matrix. It's just one number, and that product turns out to be the 1 by 1 matrix with the number 70 in it. And that's it. We're done. So the thing to note here is the product of two matrices is usually not of the same size as either of those that you started with. We started with a 1 by 4 times a 4 by 1, and we got a 1 by 1, and that is 70. Now, it's worth noting that we can sometimes reverse the order of multiplication and sometimes not, but we'll always, almost always, get a different result. So I'm going to take these same two matrices and I want you to tell me if they can be multiplied in the opposite order. Can we take 1, 2, 3, 4 and multiply it by 5, 6, 7, 8? Can we do this or not? Well, let's perform our test. The size of this matrix is 4 rows by 1 column. That's a 4 by 1. And the size of this matrix is 1 row by 4 columns. That's 1 by 4. So are the middle two numbers the same? Yes, they are. They are the same, and so that means that we can multiply. But here's what's interesting. The outer numbers tell you what size your new matrix will be. So our new matrix is going to be a 4 by 4 matrix. It's going to be big. So how do we end up with a 4 by 4 matrix? Well, to find the top left entry in our 4 by 4 matrix, we're going to take the top row here and combine it with the first column here. So the first row here combined with the first column here, that's going to be 1 by 5. For our first row, second column, we're going to take the first row here and multiply it by the second column here. That's going to be 1 by 6. Our first row, third column is the first row times the third column. That's 1 by 7. And our last column in the first row will be our first row times our last column. That's going to be 1 by 8. And pretty soon here, you're going to start to see the pattern. Our second row, we're going to take the second row and multiply it by each element. We're going to take the second row and multiply it by each column. So we're going to take 2 times 5, 2 times 6, 2 times 7, and 2 times 8. Now I'm sure you see the pattern. Third row, first column, we're going to take the third row times the first column. That's 3 times 5, and so on. 3 times 6, 3 times 7, and 3 times 8. And our last row, first column, will be our last row times our first column. 4 times 5, 4 times 6, 4 times 7, and 4 times 8. Now if we do all those products, we'll get our product matrix. And so we get 5, 6, 7, 8 in the first row, 10, 12, 14, 16 in the second row, 15, 18, 21, and 24 in the third row, and our fourth row is going to be 20, 24, 28, 32. And there it is. Sure enough, we got a 4 by 4 matrix. So it's important to always look and see whether you can do your multiplication and what the size of the result will be before you start doing any dot products or multiplication. Now that's pretty tricky, so I want to do another one with you here. We've got a 3 by 2 matrix times a 2 by 4 matrix. Is that allowed? Well, let's apply our test. 3 by 2 times 2 by 4. Those two middle numbers are the same, and so yes, we can multiply these two together. How big will our result be? it's going to be a pretty big 3 by 4 matrix, okay? So we know that this is going to be 3 rows and 4 columns, so a decent sized matrix. I'm going to leave that blank for a minute and perform the work down here because there's quite a bit of computation. So I'm going to make a big old matrix to write out our process. We'll transfer our results up here. So to find the first entry, top row, first column, we're going to take the dot product of our top row here and our first column here. That's why the row-column relationship is so important, since this is first row, first column. I'm going to combine the first row here with the first column here. So that's going to be a dot product, 5 times 5 plus 0 times 2, which of course is 25 plus 0, so our top left entry is 25. Okay, for our next entry, it's going to be first row, second column. First row, second column means I'm going to combine the first row here with the second column here in order. So that's going to be 5 times 6 plus 0 times 0, which is, of course, 30 plus 0. The next entry is 30. We're taking, again, a dot product there. First row, third column. I'm going to dot product the first row with the third column, where I'm ultimately just timming it down, so that becomes 5 times 7 plus 0 times negative 1. And that is, of course, 35 plus 0. Our next entry is 35. And our first row, last column means I'm going to combine the first row and dot product that with the last column. So that's 5 times 8 and 0 times 4, which is, of course, 40 plus 0, which is 40. Okay, now I'm going to move on to the next row. For the next row, this spot right here, for example, I want to combine the second row, first column. So I'm going to take the second row here and dot product that with the first column here. So that's going to be 1 times 5 plus 4 times 2, which is 5 plus 8. Our entry there is 13. Next position will be second row, second column. So I want to combine the second row with the second column. That's going to be 1 times 6 plus 4 times 0, which is, of course, 6 plus 0. That entry is 6. Let's finish out the row. Second row, third column. Combine the second row with the third column. That's 1 times 7 plus 4 times negative 1. 7 plus a negative 4 is just 3. And for the second row, last column, we'll combine the second row with the last column here using a dot product. 1 times 8 plus 4 times 4. And so that becomes 8 plus 16. Our last entry in that row is 24. Okay, for our third row, first column, I want to find the dot product of the third row here by the first column here. So negative 2, 6, and 5, 2, that becomes negative 2 times 5 plus 6 times 2. And that's, of course, negative 10 plus 12. That entry is 2. Third row, second column. Combine the third row with the second column. That's going to be negative 2 times 6 plus 6 times 0. Or in other words, negative 12. Third row, third column. Combine the third row with the third column. That's negative 2 times 7 plus 6 times negative 1. Negative 14 minus 6 gives us negative 20. And last row, last column. Combine our last row with our last column. That's going to be negative 2 times 8 plus 6 times 4. So that's negative 16 plus 24. Our result there is 8. And there is our 3 by 4 matrix, which is our product. Now, matrix operations are easily done by a lot of calculators. There's apps that do this. but the fundamentals of how it's done are going to be important for some other reasons. So make sure that you make sense of that skill, rewind if you need to watch that explanation again, but let's reverse the order here and see what happens. Okay, let's try reversing the order. So we have a 2 by 4 matrix here, and here we have a 3 by 2 matrix. So notice that we have a problem here. These two middle entries, 4 and 3, do not match, and so we cannot perform this multiplication. And you can probably see why. Even if we wanted to, even if we wanted to create a matrix out of these two, supposedly it would be a 2 by 2 matrix, but that's not going to work out. And even if we wanted to find the dot product, to find the top left entry, we would take our top row and combine it with the left entry. But there's 4 values here, but only 3 in this column, so we can't take a dot product of 4 numbers versus 3 numbers, and so for all kinds of reasons, it just doesn't work when the two middle numbers don't match. And so we can't multiply those two matrices in the opposite direction. That's something that's unique about matrix multiplication, is that you can multiply matrices one way and get a result, but the other way you don't. Okay, so I want to show you why matrix multiplication is such a convoluted process through an actual simple application here. Suppose you had a concession stand at an event that had 3 cash registers, and they were selling drinks, hot dogs, popcorn, and candy. And so I've given you a table with the sales figure here. Register number 1 sold 9 drinks and 6 hot dogs, 10 popcorns, and 4 candy, and so on. Drinks are $1 a piece, hot dogs are $3, popcorn is $2, and candy is also $2. Let's use matrix multiplication to see what the sales are at each of the registers. Well, you certainly could perform a whole bunch of individual multiplications here to get that total, and that's ultimately what we'll do, but we're going to do it using a matrix. So notice that the register number really isn't important here. That's not actual data. That's just telling us what the numbers are, just like drinks, hot dogs, popcorn, and candy. So I've taken the sales figures here and put them into this matrix on the left, and that is, after all, 3 rows by 4 columns. That's a 3 by 4 matrix. The prices, given in the same order as they were in the column, drinks, hot dogs, popcorn, candy, is a 4-row by 1 column matrix. So since these middle numbers do match, we can in fact multiply these together. And our result is going to be, as you can see, a 3 by 1 matrix. So let's perform this multiplication. Here again, I'm going to put the result here, but I'm going to make a big matrix to calculate our result down here so we actually have a space to do our work. Knowing that this is going to be a 3 by 1 matrix, that means we're going to have only 1 column, but 3 rows. So here we go. We're going to take, for our first row, first column entry, I'm going to take the first row here and combine it with the first and only column here. So that's going to be 9 times 6, 6 times 3, 10 times 4, and 4 times 2, a dot product. So here we go. 9 times 1 plus 6 times 3 plus 10 times 2 plus 4 times 2. And if you do the math there, this is really 9 plus 18 plus 20 plus 8. And if you add all those up, you end up with 55. Okay, to get our second row, first column entry, there is only 1 column, so that's the only column we can do. We're going to find the dot product of our second row with our first column. So that's going to be 11 times 1, 9 times 3, 10 times 2, and 2 times 2. When we do that, we get 11 plus 27 plus 20 plus 4, and if we add all those together, we get 62. To get our third row, first column entry, we're going to find the dot product of our third row and our first and only column. So that's going to be 6 times 1, 8 times 3, 11 times 6, and 6 times 2. 6 plus 24 plus 22 plus 12 gives us 64. And then our result, as you can see, is that our first register sold $55 worth of products, our second register sold 62, and our third register sold 64. And that information is neatly arranged in a 3x1 matrix. Now, if you tried to reverse those, you'd probably see that the inside numbers wouldn't match, and you couldn't even perform that multiplication. And so there's only one way to do this, and we're done. Okay, well that's enough for this lesson, but I would like you to just practice this before you jump into your homework. I've given you three matrices here, A times B, B times A times C, and C times A. Pause the video, perform those multiplications, and check your answers against mine to make sure you've got the hang of it here. Okay, let's take a look at our first one here, A times B. This is a 2 by 3 matrix, and we're going to multiply it by a 3 by 2 matrix. We can perform that multiplication. These two middle numbers match, and our result is going to be a 2 by 2 matrix. So we'll put our result there, though I'm going to once again do the work in this space below. So here we go, first row, first column, this top left entry, we're going to take our top row and take the dot product with the left column. That's going to be 4 times 5 plus 0 times 6 plus negative 1 times 1. I'm just going to write down 20 plus 0 minus 1. And that means our top left entry is 19. Top right entry, top row, combined with the right column. That's going to be 4 times negative 2, 0 times 3, and negative 1 times 9. I'm just going to write down negative 8 plus 0 minus 9. And so our top right entry is negative 17. Bottom left entry, we're going to combine the bottom row with the left column. The dot product there would be 3 times 5, 2 times 6, and 10 times 1. I'm going to write down 15 plus 12 plus 10. And so we get a bottom left entry of 37. The bottom right entry, we're going to combine our bottom row with the right column. 3 times negative 2, 2 times 3, and 10 times 9. That's negative 6 plus 6 plus 90, which is of course 90. And there is our 2 by 2 product matrix, and you're done. Hopefully that's what you got. Okay, what if we reverse the order? Let's take matrix B times matrix A. That's going to be a 3 by 2 matrix times a 2 by 3 matrix. We can do that. The two middle numbers match, and our result will be a 3 by 3 matrix. So it's going to be a little bigger this time. Okay, so let's do the arithmetic down in this space. So for the top left entry, I'm going to take top row times the dot product left column. 5 times 4 plus negative 2 times 3. That's 20 minus 6, 14. Top middle, we're going to take top row and middle column. That's 5 times 0 and negative 2 times 2, which is really just 0 minus 4, negative 4. If you don't follow any of these, pause the video and rewind. I'm going through these a little bit faster since we've done a few now. Top right entry, top row, right column, dot product will be 5 times negative 1 and negative 2 times 10. That's negative 5 minus 20, or in other words, negative 25 in the top right. Middle row, first column, dot product of the middle row and the first column. 6 times 4 and 3 times 3, that's 24 plus 9, 33. Middle entry, middle row, middle column, dot product. 6 times 0 and 3 times 2 is 0 plus 6. That entry is 6. Middle row, right column. Combine the middle row, right column with a dot product. That's negative 6 plus 30. 24. Bottom left, bottom row, left column. 1 times 4 and 9 times 3 is 4 plus 27. 31. Dot product of bottom row, middle column is 1 times 0 and 9 times 2, 18. And bottom right, bottom row, right column, dot product, 1 times -1, and 9 times 10, -1 plus 90 is 89, and there is our 3 by 3 product matrix. Hopefully you got that. If not, make sure you find your error. Let's wrap this up. A times C, matrix A, which is 2 by 3. Multiply that by matrix C, which is 3 by 1. The middle numbers match, 3 and 3, and our result is going to be just 2 by 1. That's going to be a pretty small matrix, 2 rows and 1 column. So let's see how we get those values, 2 rows and 1 column. So a bottom and a top. For our top entry, we're going to take the top row and find the dot product of our only column here. That's going to be 4 times 7, 0 times 8, and -1 times 9. That leaves us with a top entry of 28 plus 0 minus 9 is 19. And for our bottom entry, we're going to take the bottom row dot product with our only column. 3 times 7 is 21, 2 times 8 is 16, and 10 times 9 is 90. And so we get 37 plus 90, that's 127, and there's our 2 by 1 result. Pretty quick product there. And what about C by A? C is a 3 by 1 matrix, but A is a 2 by 3 matrix. These middle numbers do not match, and so we cannot perform this multiplication. It's impossible. There's no way to do that. And so C by A cannot be performed, and so we're done. Hopefully you got all of those results the same as mine. If not, rewatch that video and make sure to learn from any mistakes you may have made. Okay, I just want to review a couple things with you here before we close. You now know that a rectangular block of numbers like that is called an array or a matrix. If you have several of them, those are arrays or matrices. If it's just got one row or one column, we call it a vector, although we won't be using that terminology all that much. And the size of a matrix is given by the number of rows by the number of columns. You can see why now that's an important order to get correct. Although we didn't use it too much in this lesson, the notation of identifying individual elements always gives its position by its row number and its column number, either using subscripts or parentheses like we see here. And of course, two matrices are equal if they have the same elements in the same position, and the matrices are, of course, the same size. We can combine matrices by simply combining the individual elements through addition or subtraction, but only if the matrices are the same size, so that every element has a corresponding element to be combined, added, or subtracted with. And scalar multiplication simply takes all the elements of a matrix and multiplies it by a positive or negative scalar. We transpose a matrix by switching the rows and columns, and if it's not square, that will change the size of a matrix. If the matrix is square, transposing it will leave it as being square. And we use a superscript T to represent transposition. But here's where our real work was. We multiply matrices by finding a bunch of individual dot products, an entire row combined with a column. We always take a row from the left matrix and a column from the right matrix. But we can only do that if the number of columns in the first matrix matches the number of rows in the second, or in other words, if those two middle numbers match when you list their sizes. And in the coming days, we'll see some more advanced applications using matrix multiplication. So that's it for now. Go ahead and do the assigned homework. Be sure to let me know if you have questions. That's a tricky process. We can work through some dot products and some multiplications. I'm happy to do that. We're going to build on that and use those dot products in the next lesson. We'll see you there.